Yes, now we will go on where we stay in and we will learn probability density functions and consider a situation in which you are waiting for a taxi to arrive. The taxi is due to arrive within 8 minutes, but you don't know when during those 8 minutes it will arrive. The following three graphs represent three possible distributions of arrival times of the taxi. For the first one, the arrival time of the taxi is equally likely at any point within the 8 minutes. So equally likely at a possibility for the first minute and the second minute, or 1.5 minutes equal probability, and the probability is 0.125. The second graph shows the normal distributed arrival time, so the taxi is most likely to arrive near the middle of 8 minutes, where the graph peaks and less likely at either end of the 8 minutes time arrival. For the most probability, the greatest probability, the fourth minute taxi arrive, but in this point and this point very low probability. This distribution is, as you remember, normal distribution. And the third graph shows the most likely arrival time of the taxi as being between 5 minutes and 7 minutes, the period of time in which the probability is greatest. 5 minutes, between 5 minutes and 7 minutes, the greatest probability has the taxi arrive. And now let's look in more detail as just one of these graphs, the final graph in the example taxi arrival time. The area under the graph represents to the total probability of the event occurring, that is taxi arrival time. We can check that this is a probability density function by calculating the area under the whole graph. For if we compute the area under the graph, we have a trapezium graph. As you know, this distance is 8 and this distance is 7 minus 5, and it becomes 2, and our height is 0.2. If I want to area 8, if I want to compute the area, 8 plus 2 over 2 multiply height, so 0.2, and it becomes 5 multiply 0.2 and 1. And using geometry, the shape of the graph is trapezium area is become 1. Okay, now we compute the area differently, and also by using the integration, and this line gradient is the gradient is 0.04, or it becomes 1/5. So this line equation is x over 25, and this line equation, or this line formula, is also 0.2, so also 1.1/5, and this line gradient is uh, 1 point 0 point 0.2. So this line formula, or this line equation is 8 minus x over 5 if x between 7 and 8. And the other x value, the function equation, the function equals to 0, because we have only 8 minutes value. Okay, now if we use the if we want to compute the area by using integration, we should use integration from 0 to 5 x over 25 dx plus integration from 5 to 7 1 over 5 dx plus, and integration 7 to from 7 to 8 8 minus x over 5 and dx. It means, 1 over 25 multiply x square over 2 from 0 to 5 plus 1 over 5x from 5 to 7 plus, and and 8 over 5x minus, or I want to compute differently, 1 over 5 8x minus x square over 2 from 7 to 8. And if we compute this integration, and also we could find 1, and this situation shows us the probability density function. When we have the probability density function, the under the area, the sum of the under the area every time has sum of the area equals to 1 always. Okay, and a graph fx representing a continuous random variable is the probability density function. It's called PDF. The PDF has the following properties. The first one, our function is greatest than and equal 0 because it cannot be negative, and we cannot have a negative probability, and the probability of all outcomes 1. So the integration from negative infinity to positive infinity is equals to 1 every time. In many situations, the data are defined across the specified interval or across specific intervals outside of which fx becomes 0. And then the other section, calculating the probabilities. We can calculate the probability that the taxi arrival time will be in a given interval, but we cannot calculate the probability of an exact arrival time for the taxi. That is, we cannot calculate the probability of an exact outcome. For example, consider that we have two runners. The first one from Kenya, Lorna, from Kenya, Tegla, and from Holland or Netherlands, Lorna. And their lifetime best performance are both 10 minutes 37.26, 30 minutes and 37.26 seconds, but do they really have exactly the same lifetime best performance time? Performance time is given correct to the nearest hundredth of a second. The actual time may have been, for example, 30 minutes 37.26264, or 30 minutes 37 seconds 259, or 256111, or infinitive. The possibility are infinitive. The performance time 30 minutes point 37 point, or actually range of the times from 255 to 265. So it follows that with a continuous random variable we can only calculate the probability of range of values. We can, please notice that we can only calculate the probability of range of values. We can't calculate the exactly values probability. We can only calculate the probability of range of values, not exact value. And with continuous random variables, each individual values has zero probability of occurring. For a continuous random variable with PDF, if we want to compute the exactly value probability becomes zero, because we cannot find probability of an exact value. When finding the probability in a given interval, it doesn't matter you use your sign has equal sign or not, it doesn't matter. So these process also equals each other. X greatest than A less than B, or X greatest and equals than A less than B, or X greatest than A less and equals than B. It's also the same, because the probability of A exactly A, for example, or B, zero. So it doesn't matter equal sign we have or not. Okay. Now, to find the probability within a specific interval, we use calculus, more specifically integration, or sometimes geometry. Let us consider again the final graph in the same taxi arrival time. If we want to find the probability that the taxi arrives between 4 minutes and 6 minutes, then the shaded area, the following graph, represents this possibility. And also you can compute these area by using the geometry. And you have trapezium, and this distance 2 and this distance is like 0.16, and this distance like 0.20, and you have both rectangle and trapezium. So if you want to compute the trapezium area, you should 0.2 or 20 plus 0.16 over 2 multiply height. So this height is 1 multiply 1, plus this rectangle area is 1 multiply the other side 0.20, and also we have 0.38 it means the probability of x greater than 4, less than 6. And if you want to probability, if you want to compute the probability by using integration, you need to have these line equation and these line equation. So these line gradient is for example this side over this side, and it means tangent, gradient is 0.20 over 5, so 1 over 25, and this line equation is x over 25, and this line equation is this 1 over 5, or it means 0.2 when x greater than 5, less than 7. And the other one, but we don't need to this line equation, but this equation gradient is 0.2 over 1, it becomes 1 over 5, but we have range, so it should be minus. So this line equation is 8 minus x over 5 when x 7 greater 7 less than 8. If you want to compute the area by using integration, we should use this formula: integration from 4 to 6, and the probability density function multiply dx, it equals to also 0 from 4 to 5 fx dx plus from 5 to 6 fx dx. Okay, now and we have these integration from 4 to 5 x over 25 dx plus the integration 5 from 5 to 6 1 over 5 dx. And now this integration equals to 1 over 25 multiply x squared over 2 from 4 to 5 plus 1 over 5x from 5 to 6, and it means also the same with before value, the first one by we used to geometry, and the second one we use the integration. So the probability of x lying in the interval a and b is given by the area under the graph between a and b. This is our formula for the probability density function for integration. Now we will compute the example, and I hope you can understand the easily probability density function. The height reached by water erupting from a broken water pipe x meters is modeled by the following PDF. Our PDF here show that key equals to 333. So please remember that the integration from 1 to 10, and the sum of the all the sum of the under the curve, under the graph area should be 1. So the integration from 1 to 10 fx should be 1. So the integration from 1 to 10 x square over key dx, and it means 1 over key multiply x cubed over 3, 1 from 1 to 10, and 1 over key means 1000 over 3 minus 1 over 3 should be 300 should be, excuse me, should be 1, because the under the graph area should be 1 in a probability density function. So and it becomes 1 over key 333 equals to 1, and key should be 333. And the other section, sketch the graph of x. Please remember that x square graph. X square graph means means these curve, and our x 1 between 1 and 10, this area. Okay, now this area. Okay, this graph related to fx they give us the formula. The otherwise is 0, so it should be, the otherwise it's 0, it should be only these section, only these area, because for the other y's, for the other x values, our function is 0. So we should draw the curve between 1 to 1 and 10, because the other y's for x value, our function equals to 0. Okay, find the probability that the water reaches the height of at least 6 meter. At least 6 meter means the probability of this area. So we should find the probability of greatest than x greatest than 6, less than 10. And please remember that we can put the sign, equal sign, or not. It doesn't matter in the probability density function, because exactly the probability of exactly value is 0. So it doesn't matter you put a sign or not. Okay, and it means integration from 6 to 10 fx dx, and means x over x square over key is, please remember that 333, and 6 to 10 x square over 333 dx, and it becomes 1 over 333 x cubed over 3 and 6 from 6 to 10, and 1 over 999 multiply 1000 minus 216 and it means 784 over 999. I want to compute the approximately value for the process, for this process, and 784 over 999, it becomes 0 point approximately 78, 0 point approximately 78. Okay. Now in this lesson we have no time, and we finished for now. For now our lesson is finished. So the other lesson we will go on where we stay in. Okay, have a good day, and have a good lesson.